The rate of reaction between calcium carbonate and hydrochloric acid is investigated using continuous monitoring method. So this is an acid plus a carbonate makes a salt plus water plus carbon dioxide. They're going to place a conical flask on a balance and they're going to add approximately 20 grams of calcium carbonate marble chips and then the hydrochloric acid. Place a loose cotton wool bud in the neck of the flask, zero the mass reading on the balance and start the timer. Record the loss in mass, MT, every 30 seconds for 4 minutes and wait for the reaction to finish and record the total mass loss. Plot a graph of M total minus MT against time. Graph shows results obtained during the first 240 seconds. So the total mass loss here looks like it was 38 at 0.38 grams, and then they're subtracting the amount lost over time, and so it's decreasing the first sort of 4 minutes here. Suggest why a loose cotton wool plug is placed instead of leaving it open or inserting a bung. So the idea is that cotton wool is going to allow gas to escape without letting liquid escape. So instead of leaving the flask open, this avoids the solution escaping, the liquid escaping from the flask. But instead of inserting a bung, it allows CO2 gas to escape. "20 grams of marble chips is a large excess of calcium carbonate. Suggests why using a large excess means that the rate is only affected by the change in concentration of hydrochloric acid." Well, when we have a large excess, so that we've got loads of calcium carbonate and only a little bit of HCl, then when all the HCl gets used up, it uses up some of the calcium carbonate, but it's such a small amount that the calcium carbonate has stayed effectively constant. So rate is only affected by concentration of HCl because the amount of calcium carbonate is a constant. So we need to be clear though, because calcium carbonate is a solid, so we want to say so that the mass is effectively constant. Don't say the concentration here because it was a solid, and rate is only affected by concentration of HCl. The mass of carbon dioxide produced in time t is equal to MT. The total mass of CO2 is equal to M total. Explain why M total minus MT is proportional to the concentration of hydrochloric acid remaining in the flask at time t. So this is a tiny bit tricky, but if you think about the equation again and you try to understand what they're asking, so the mass of carbon dioxide produced at time t, the mass of carbon dioxide will be proportional to the number of moles of carbon dioxide. And if we look at this balanced equation, for every 2 hydrochloric acids, we make 1 CO2. So let's say we start the reaction off, just for argument's sake, with 10 HCl's, we'll have no CO2s. And then after a little bit of time, if this has gone down to 8, this will have gone up. So this has changed by, we've used up 2, we'll have made 1. And then if we use up another 2, we'll have made another 1. And another 2, we'll have made another 1. And another 2, we'll have made another 1. And so on until all the HCl is used up and we've made CO2. So the mass of CO2 produced is proportional to the amount of HCl that has reacted because of the ratio of the balanced equation. So the mass of CO2 produced at time t is, so that's the MT thing, so is proportional to the amount of HCl that has reacted because, as we can see here, as 2 had reacted, then 4, then 6, then 8, then 10, we'd gone 1, 2, 3, 4, 5 because of the ratio. So it was proportional to the amount of HCl that had reacted. The M total, the total mass of CO2 produced, is proportional to the total amount of HCl that had reacted. So we got down to 0, we'd made 5. So M total minus MT is proportional to the HCl remaining, because it's proportional to total HCl minus HCl that has reacted. Table 1 shows the rate of reaction calculated from the gradient of the curve at 5 different times. Remembering that this is a measure, essentially, M total minus T is proportional to the concentration of HCl. So it's essentially a concentration time graph for HCl that we're drawing here. We've got some values and we have to plot them onto the axes. So we're going to have to draw our axes ourselves. We want rate up the side and concentration of HCl along the bottom. And the concentration of HCl is the M total minus MT. So we want the M total minus MT, and the units are in grams along the bottom. And then up the side we want rate in grams per second. And looking at the numbers, we need to go up the side to our biggest number, 23, from 6.67 times 10 to the minus 4 to 23. So we need to get up to 23, and we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 big squares. So it would make sense to go up as in 2s times 10 to the minus 4s. So if we went, let's put the times 10 to the minus 4 up here. So we go 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. That will allow us to plot all the numbers up to 23 times 10 to the minus 4. And then along the bottom, we need to go from 0.1, being our smallest, to 0.34. And we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 squares. So if we see how that, if we were to do 0.025s on 14 squares, it will take us to 35. So you don't want to come up with a silly scale, so don't divide it completely up. I'm going to go 0.25s. I'm just going to mark every second one though. They're 0.05s, so that we can go 0.1, 0.15, 0.2, 0.25, 0.3, 0.35, and then we can plot our first point. So at 0, 0.34, we're at 23. So given that our scale has got 10 little squares for 0, 0, 5, 3, 4 is 2 little squares back, 23 is halfway between 22 and 24, so right up here. And then 2, 8, so 2, 7, 5, 2, 8 would be 1 square after this middle bit, and we want to go up to 19. And then we want to go 0.225, which is this middle line here, and 15.7, so 14, 15.26, just above there, 15.7, and then 11.5 at 0.17, 11 here, 11.2, 11.6, 11.5 at 0.17, and then at 0.1, 6.67, so 6.4 and then 8, 6.67 would be in between. So I've plotted my points, and now I need to use a ruler to draw a line of best fit through these points. Now, it looks like this is going to go through the origin. Remembering that when drawing a line of best fit, if they're not all going to lie on the line, you need to have equal points above and below the line. Although on this one we do seem to just have 1 point slightly below the line. Sorry, above the line even. But you can see I've got the top point just slightly above, the next one slightly below, the next one slightly above, slightly below, and slightly below. I've done an even spread either side of the line. State how the graph confirms that this is the rate equation. Well, the graph shows that because it's a straight line through the origin. That shows its first order. In this experiment, the variable measured is mass loss. The rate of this reaction can be investigated in other ways. State 2 other variables that could be measured instead of mass lost. We could have attached a gas syringe and measured the volume of gas produced, CO2 in this case. We were using an excess of calcium carbonate, so we were using up all our hydrochloric acid, so we could have measured the pH over time as well.